Today we will wrap up this discussion of statements equivalent to the prime number theorem. So I had this diagram the other day that was how we were going to go. Anyway, this is statements equivalent. So this equivalent is meant in the sense of elementarily equivalent to the prime number theorem. Right? So the statements are, so you have phi of x asymptotic to x over log x. That's the classical PNT. That's, of course, equivalent to the weighted version psi of x asymptotic to x or theta of x asymptotic to x. Okay. Either way. And then we have one more here. L of x is little o of x log x. And I will write down L of x for you. L of x is summation mu of n log n. This by itself is not so interesting, but it acts as a go-between. Okay, so we are really interested in m of x equal to little o of x. So these two are equivalent. And m of x is the sum of the Mobius function up to x. This is an interesting probabilistic thing. And then finally, we have a striking evaluation, namely the summation mu of n over n, n from 1 to infinity, is 0. And the statement m of x, little o of x, is actually equivalent to mu of n over n equal to 0. So the way so they're all equivalent. So the way we're going to prove this is clear. The other day we went from psi of x asymptotic to x to L of x, little o of x log x. This is going to give me this, so we're going to go in this direction today. And then finally we're going to come from m of x equal to little o of x to psi of x asymptotic to x. And this I will show on the side. It's got some interesting features of its own. Okay, so psi of x asymptotic to x implies L of x equal to little o x over log x done. Okay, so now we'll go to our next theorem today. So, one, L of x is little o of x log x implies m of x is little o of x. So as I said, the L of x log x is sort of like an intermediate thing. It helps us. The reason being, mu of n log n is the summation of that over the divisors is what gives you the von Mangold lambda function. And the sum of the von Mangold lambda function is what gives you the psi function. And therefore, it's natural to connect this with that. But now let us do this. All right. Sorry. So proof. Okay, so we just use other here. So we write summation m of x, which is the sum of the Mobius function up to x, as summation mu of n log n divided by log n. Well, you will of course object to this, so it is 1 plus, and then this is 2 less than or equal to n less than or equal to x. We can ignore the 1, I mean that has no consequence on the little o of x. So ignoring this, so this is 1 plus. This part we can write as integral from 2 minus to x of 1 over log t dl of t. Right? The jumps of the L function are mu n log n. So we integrate this by parts. Evaluation, so this is 1 plus, and now I have got L of t over log t from 2 minus to x minus the integral from 2 to x L of t dt. Now the derivative of log t to the minus 1 is minus 1 over log t to the minus 2, and then another t. Okay, so this is, at the upper limit, this is little o of x log x divided by log x, so we got little o of x coming from this. As far as this is concerned, this is the integral from 2 to x. Now there are many, you can do this in a very simple way. This is really not going to contribute much, because even if I use the simple upper bound that little o of x log x is the same, it implies capital O of x log x, then I can replace this with capital O of t log t. That kills the t, it kills 1 log t. So this is capital O of dt over log t. This is your logarithmic integral of x, which, as we observed yesterday when we do integration by part, is x over log x plus x over log squared x plus 2 factorial x over log cubed x, dot, dot, dot. You can chop it off at any stage, and then you get x over log x to the k part. So this is of order of magnitude x over log x. I'm just noting this. I don't need it this sharp. Actually, it's little o, because I've only used L of t equal to capital. If I put little o, I'll get this. So anyway, the entire thing is little o. So this is easy. But now we need an idea to go from m of x equal to little o of x to psi of x asymptotic to x. Okay, so the next thing. M of x equal to little o of x implies psi of x is asymptotic to x. So this is going to require some idea, meaning they've got to introduce a suitable function. Okay. All right, so here's what we do. So, begin by observing that, this is quite interesting. We look at x, we subtract psi of x, and then we subtract a 2 gamma Euler's constant, which, like we did before, but it looks kind of innocuous, because x and psi of x are so big, what's this constant going to do? But it's going to help us in terms of the summation using the x. So what is this? So the way I think of doing this, we first think of the x minus psi of x as, we think of x as an integer, okay? It's the sum of 1 minus lambda m. Because the sum of 1 over numbers up to x is x, the sum of the lambda n up to x is psi of x, minus 2 gamma. Okay. Now, what do we do? We're going to write this as a summation over divisors. It's a summation over d n less than or equal to x of a summation over all divisors of n. Now, I'm going to put something, and I will justify in a moment. Tau is not the Ramanujan tau function, it's going to be the number of divisors function. And I'm going to put mu of d, tau of n over d, minus log of n over d, minus 2 gamma. So now let us justify this. So this is going to be equation 1. Why is this the case? Because what is tau of n? Tau of n is the number of divisors of n. So it is the summation of 1 over d dividing n. So applying the Mobius inversion formula to this will give me 1 is summation mu d tau of n over d. That is by Mobius inversion, right? So I have taken this number 1, and I have represented it as summation d dividing n mu d tau of n over d. That's what I have done here. So that explains why we have brought in the tau function in there for that. So that represents 1. Now what about the lambda function? Log n is summation log d, d dividing n. This we have already used, and therefore log n is summation, sorry. Lambda d. Therefore, lambda n is summation mu d log of n over d dividing n. But again, by Mobius. So I'm interpreting this minus log n as minus summation mu d log n over d. And finally, summation mu d d dividing n is 1 if n is 1 and 0 if n is greater than 1. Therefore, this last sum, forget this as a constant, is simply this over, if I put a 1 here, would be simply this number at 1 and 0. So it'll only give me the value 1. So if I multiply by 2 gamma, it just gives me the value 2 gamma. So I'm just giving the reasons for writing it that way. So this is the ideal. I mean, we bring in the 1 and the lambda and then subtract off the 2 gamma. All right, so now put f of n to be tau of n minus log n minus 2 gamma, or this constant. So what do we know about tau of n? Then summation f of n, n less than or equal to x, is the sum of the divisor function up to x minus the sum of the log n up to x minus 2 gamma x. Right? And so what is this? The sum of the divisor function up to x, that's what was the Dirichlet divisor thing. So that's x log x plus 2 gamma minus 1 times x plus capital O plus square root of x. That came from Dirichlet. This is the sum of the divisor function of x by the hyperbola method. The first time we used the hyperbola method was to get this Dirichlet thing, and we used this trick that the number of divisors is 2 times the number of divisors of n which are less than square root of x, and the error comes precisely when you have these perfect squares. So this square root is one of the reasons for the square root is from the perfect squares. Okay, the log n, sum of the log n of is x log x minus x plus O of log x. That's this. And finally, minus 2 gamma x. So what do you get there? So your x log x cancels. Your plus x cancels the minus x. And then 2 gamma x cancels the 2 gamma x. So you end up with square root of x. Therefore, the sum of the f's, n less than or equal to x, is O of square root of x. So this is a very good cancellation. Tau of n minus log n minus 2 gamma is about square root of x.
What about O log x?
That's absorbed in O square root of x. Smaller in magnitude compared to square root. So if you want, you can say, on average, the number of divisors is like log n plus 2 gamma. I mean, there the 2 gamma mix is important, because without the 2 gamma, that difference will be of order of magnitude x. which is still okay because that is still small compared to x log x, but this is much smaller compared to x log x. Right, so that 2 gamma plays a role. Okay, so the sum of the f is capital O of square root of x. Okay, very good. Now put, maybe I can put that here. Capital F of x is the sum. This is defined to be the sum. So I've got a colon here. This capital F square root of x. Okay. So now what we do is, so let us rewrite 1 as, so in view of 2, so rewrite 1 as follows. X minus psi of x minus 2 gamma is equal to summation n less or equal to x summation d dividing n mu d f of n over d, right? So that's what we have done here, except I've got an estimate here, which by the hyperbola method is equal to summation mu of n, if you want you can put mu of j, f of x over j less than or equal to sum a, plus, I put a b here, plus summation f of k, m of x over k less than or equal to a, minus m of d, f of a. Right? So this was the, where a and b will be chosen suitably. Where ab is equal to x, the product of a times b will be x, and a and b will be chosen suitably. Right, so just to remind you, this is the hyperbola. So we are thinking of this hyperbola as yz equal to x, y-axis is the axis. So I've got any lattice point here. I'm thinking of it as a mu d f of, this is the lattice point, whose coordinates are d comma n over d. That product is n is less than or equal to x, so that's the area underneath the hyperbola, the region underneath the hyperbola. So I'm evaluating the mu function here, and then the n over d function here. Therefore, I'm thinking, my apologies, I'm thinking of this as b and this as a. Sorry that I haven't written it that way. So what I'm doing is, I'm doing the j running from 1 to b, and then I'm evaluating the sum of the f's. That's the capital F. That goes up to x over j when the product is x. Then I'm doing the f function, which is the n over d, from k to k, it goes from 1 to a, and then I'm doing the sum of the Mobius function. But then the overlap has been done twice. So in the overlap, it's just the product of n of b. Okay, so we've done this before, but a, b equal to x, and a and b will be chosen 0. All right, so how do we choose the a and b? Now consider the sum so let's epsilon greater than 0 be given. Okay. So consider first summation mu j f of x over j. j less than or equal to b. Now, what do you know about capital F? Well, the capital F is no more than the square root. But when I put the capital O, I lose control over the sign changes of the Mobius function. But I can use the fact that the Mobius function is no more than 1. So this is capital O of summation of the square root of x over j, j less than or equal to b, by 2. Okay? So the square root of x comes out, and then I am summing 1 over, 1 over j, square root, j less than or equal to b. Now, what do we know about the sum of the reciprocals of the square roots? You can use you can use integration. So summation dt over square root of t, which is t to the minus half, is t to the 1/2 or 1/2. So it's 2t to the 1/2. So it's 2 times a to the 1/2. But I'm putting this as capital O of the square root of x times b. But that implicit constant is absolute. This implicit constant is coming from the absolute implicit constant coming from here. An absolute constant, a, whatever it is, an absolute constant. And I'm now multiplying that by 2, because it's really 2 times square root of b, right? I'm multiplying that by 2. So this is some implicit constant, whatever that constant is. So it's a capital of x square root of b. But what do we know about so square root of x? AB is equal to x. So square root of a, square root of b is square root of x. So square root of b is square root of x divided by square root of x. So I'm going to think of this as square root of x divided by square root of a. Okay. So 3. So in 3, we choose A, or not in 3, in view of 3, not just in 3. 4, thank you. In view of 4, we choose A to be some constant over epsilon squared. That constant is an absolute constant. The reason is, so what is this constant? So this constant is to get this sum. Exactly epsilon x. So you see, if I choose A to be c over epsilon squared, epsilon will come out. This, so x times, no, this is a mistake. It's this. There's another square root coming from the b. Square root of x over square root. This is x. There's no square root at the top. It's x over square root of x. Okay, so I choose A to be c over epsilon squared, so that I will get an epsilon there. There is some c, but that c will annul the implicit constant here to give me 1. That's what I mean by the choice of the c. I choose the c to kill the implicit constant, whatever that implicit constant, reciprocal of that implicit constant. Or maybe I should say the square reciprocal or something, because that c is going to come in. Anyway, you understand what c is. All right, so this is less than epsilon x. Good, so this is 5. All right, so now what we do is this. Epsilon greater than 0 is given arbitrarily. Okay, so epsilon greater than 0 is arbitrary, but now it is fixed for the rest of the proof, until the proof is completed. Which means b, which is x over a, is tending to infinity with x. That's important. Why is that important? Because in the second sum, I have x over k, and k is less than or equal to a. So the smallest value of the argument for the m function will be x over a. But x over a is a b. But that b is now tending to infinity with x. Therefore, I can apply that the m function is little o of whatever the argument is, because m of x is little o of x is valid as x goes to infinity. So that's the main thing, right? This means okay, so let this happen. We also know that m of x is less than epsilon x for x greater than some x naught of epsilon. Therefore, this second sum is less than or equal to, I'll pull that epsilon out. But now I have to put absolute values. I'll pull the x out. But now I have to put absolute value of f of k divided by k. K less than or equal to a, provided if x over a is greater than or equal to x naught of epsilon. I can apply this so long as this argument is bigger than x naught of epsilon, which is the same as saying that x is greater than or equal to a times x naught of epsilon. So this is what sufficiently large means. I mean, x is going to infinity, so I'm now only going to look at values x, which are bigger than this value. But epsilon is arbitrary, but it is fixed till the proof is completed. Choose an epsilon. With respect to this epsilon, I'll show that the lim sup is less than epsilon, but epsilon is arbitrary. Okay, so for x greater than a times x naught of epsilon. But now what can you say about f of k over k? The f function has, what is the definition of the f function? It is the number of divisors minus the logarithm minus 2 gamma. Therefore, the sum of the f function is at most an absolute value, the sum of tau of n over n, log n over n, 2 gamma over n. Okay, so this is what the absolute root says. Observe that summation absolute value of f of k over k less than or equal to a, is less than or equal to summation tau of n over n, tau of k over k less than or equal to a, plus summation log k over k, plus summation 2 gamma over k. Now, the summation 2 gamma over k is of order of magnitude 2 gamma log a. A is going to infinity. A is large. What is A? A is c over epsilon squared. Epsilon is small. So this is of order of magnitude log a. This is a log k over k. So this is of order of magnitude log squared k. This average, the number of the divisors, is itself like the logarithm function. It's like x log x. So the average value of the number of divisors is like log. So when I do d of n over n, that's going to be of size log squared. They're all of size log squared. So except the last one. So this is capital O of log squared a. Implicit constant is absolute. There's some absolute constant, 7. Therefore, by 6 and 7, we have the sum, the second sum, f of k, m of x of k less than or equal to a, is capital O, implicit constant, epsilon x log squared a But what is A? A is C over epsilon squared. So this is capital O of epsilon x log epsilon. Absolute value. It's the absolute value of epsilon because epsilon is equal to 0. So log epsilon is going to be negative, but it's absolute value. A is like epsilon squared, 1 over epsilon. Okay, so this is what I have. We'll call it 8. So we're done. Finally, we have to deal with M of B, F of A. M of B, F of A is capital O. If you want, you can put M of B as just B with implicit constant 1. And F of A is of the order of magnitude square root of A. So AB is X. And so this is capital O of epsilon X because I've chosen A to be of the order of magnitude epsilon squared. These are all absolute constants. Well, this alone depends upon that. Okay. So it's capital of epsilon X. So this yields what? X minus psi of x, an absolute value, forget about the 2 down now, this is capital O of epsilon x, and epsilon x log epsilon. Now we use the property of that epsilon log epsilon tends to 0 as epsilon tends to 0. See, this is tending to 0 and this is tending to infinity, but this is tending to 0 much faster than this is tending to infinity, because if you want, you can write this as log epsilon divided by 1 over epsilon. This is going to be infinity much faster than log epsilon to infinity. You will load it all whatever you like. This is going to 0. Hence, psi of x is asymptotic to x because these are quantities that are tending to 0. So it's little over x. Since this is true for every epsilon greater than 0. Right. Well, you have to be a little bit careful. I mean, there's an implicit. What we are saying is the lim sup of this is no more than epsilon log epsilon. So that's the proof that psi of x is asymptotic to x. So that completes that. Now, this m of x is a very interesting function. It dominates the theory of the Riemann zeta function because it is its generating function is the reciprocal of zeta s, and therefore it has information about the zeros of the Riemann zeta function built into it. Okay. So let's look at this statement here. That